Now, let us go over the various hardware and software components that are present in the system. This is the TI Stellaris LM3S 9B96DK platform. And the hardware stack that you see here is basically the Zigbee DODEC card that enables wireless communication. There is a custom interface board down below here, which contains some signal conditioning circuitry and the motor driver, the H-bridge driver, that's required to drive the DC motors. The processor runs the Nucleus real-time operating system, and the controller for the self-balancing robot is basically implemented as a Nucleus software application that runs on the processor. The input parameters to the controller are basically the angular rate data that is measured using the gyroscopic sensor here. This is the MEMS gyroscope that measures the angular rate on either direction. The angular rate data is integrated over time to get the pitch angle. The pitch angle is nothing but the deviation of the body of the robot from perfect vertical. The other input parameter is the motor's position, or the wheel's position, I would say. These are Lego DC motors, which are basically servo motors that come with quadrature encoders coupled with the shafts. The quadrature encoders basically provide a measurement of the wheel position. So the controller takes in these input parameters and computes a control action that is provided through a PWM signal from the processor to the DC motors. On the remote controller side, again, we have Nucleus real-time kernel running on this processor. It's the same exact processor on the Development platform. We are using TI's Zigbee Z-Stack on both the robotic side and also the controller side for Zigbee wireless communication. The other products that are used here are basically the Nucleus graphics to enable the UI and Nucleus touch panel drivers to enable the user interface.